All right, let's talk about something that feels like it's been ripped straight out of a sci-fi movie, but is actually a core truth of our universe. We're diving into time dilation. We're going to explore this wild idea that time isn't some constant universal clock, but something that can actually stretch, shrink, and, well, bend.
Okay, let's just rip the Band-Aid off and get right to the heart of it with this one sentence. The faster you move through space, the slower you move through time. Now, I know that statement probably goes against every single instinct you have about how the world works. But stick with me, because by the end of this, you'll see exactly why it's not just possible, but absolutely true.
So where does this all come from? Well, our story doesn't start in some high-tech laboratory. It starts in the mind of a young patent clerk in Bern, Switzerland, back in 1905. His name was Albert Einstein, and after a long day of reviewing inventions, he would think about the biggest puzzles in the universe. And one evening, on his tram ride home, he had an idea that would completely change physics forever.
So let's get into his first big thought experiment. This is really where the whole journey to understanding time dilation kicks off.
So as his tram was pulling away from the city's big, famous clock tower, Einstein asked himself this simple yet totally impossible question. What if this tram I'm on was moving at the speed of light? You know, a mind-boggling 186,000 miles per second. What would I actually see if I looked back at that clock?
And this led to a pretty stunning realization. If he were traveling at the speed of light, he'd basically be keeping pace with the light bouncing off the clock's face. So to him, the clock's hands would look completely frozen, stopped. But, and this is the crazy part, he knew that for everyone back at the tower, time was just ticking along normally. For him, time had slowed to a dead stop, while for everyone else, it hadn't.
Now this wasn't just some random shower thought. Einstein was trying to solve a huge problem at the very heart of physics, a kind of standoff between two of the greatest scientific minds in history. And this is the fundamental conflict he was staring down. On one side, you have Sir Isaac Newton, who basically said all speed is relative, right? How fast something is going depends on your own point of view. But on the other side, you have James Clerk Maxwell, whose amazing work on electromagnetism showed that the speed of light is an absolute constant. It's the same for everybody, no matter how they're moving. So how can both of these things be true? They seem to completely contradict each other.
Newton's idea is pretty intuitive. I mean, it's just common sense. Look at this. If a train is going 40 kilometers an hour and you're just standing there, you see it going 40. But if you're on another train going 20 in the same direction, that first train only looks like it's going 20 relative to you. Simple enough, right?
But here's the troublemaker. Light. According to Maxwell, light doesn't play by Newton's rules. It doesn't matter if you're standing still, on a train, or in a spaceship flying at half the speed of light. If you pull out a device and measure the speed of a beam of light, you will always get this exact same number. Always. This was the cosmic dilemma that kept Einstein up at night.
So, how did he solve this seemingly unsolvable problem? Well, with another brilliant thought experiment. This brings us to his lightning bolt solution.
Okay, picture this. You're standing on a train platform, right in the exact middle of 2 points. At the very same moment, lightning strikes both of those points. Since you're perfectly in the middle, the light from each flash travels the same distance and reaches your eyes at the exact same time. From your point of view, they were simultaneous.
But now, let's say your friend is on a train that's speeding past you at that very moment. As the lightning strikes, your friend is moving towards one of the flashes and away from the other. And since we know the speed of light is always constant for everyone, the light from the flash they're moving towards has to reach them first. So for them, the strikes were not simultaneous. So who's right? You who saw them at the same time, or your friend who saw one before the other? Incredibly, the answer is you're both right. But for that to be possible, something really fundamental about the universe has to give.
And this is where Einstein's radical solution comes in. He realized that for the speed of light to be constant for both people, something else had to be flexible, and that something was time itself. For your friend on the train, time must literally slow down just enough to make sure their measurement of the speed of light comes out exactly the same as yours. That is time dilation. This mind-bending realization that time is malleable, not fixed, led Einstein to an even bigger idea, that space and time aren't two separate things at all. They're actually woven together into a single, four-dimensional fabric.
The classic trampoline analogy is still the best way to visualize this. So imagine the universe is a giant, flat trampoline. That's space-time.
Now, you place a heavy bowling ball, that's our sun, right in the middle. What happens? It creates a deep curve, a big dent in the fabric. Then, if you roll a little marble, that's the Earth, nearby, it doesn't get pulled towards the bowling ball by some mysterious force. No, it simply follows the curve that the bowling ball made in the trampoline. It's falling into an orbit. That curve is gravity.
So get this. This changes everything we thought we knew about gravity. We feel like we're being pulled down to the ground. But what's really happening is that the Earth's huge mass has created such a big dent in space-time that the fabric is actually pushing down on us from all directions, pinning us to the surface. It's a push, not a pull.
So we've got two big ideas now. Moving fast slows down time, and gravity is just the curvature of space-time. Now let's connect those two and see exactly how and why time actually bends.
To understand this, let's build the simplest clock imaginable. I mean it. It's just two mirrors facing each other with a single particle of light, a photon, bouncing perfectly between them. Every time that photon hits a mirror, that's one tick of our clock. Tick, tock, tick, tock. Super simple.
But what happens if this super simple clock starts moving? Well, from an outside perspective, that photon isn't just going straight up and down anymore. As the clock moves sideways, the photon has to travel a longer, diagonal, triangular path to get from one mirror to the other. And here is the absolute key. We know the speed of light never changes, but the distance the photon has to travel for each tick is now longer. So what does that mean? It means each tick must take more time. For that moving clock, time itself has slowed down.
And this is what brings it all home. Remember that marble falling into the trampoline's curve? It's accelerating. Gravity is acceleration. You are constantly accelerating, or falling, through space-time. And since we just proved that motion through space slows down time, it means that the stronger the gravity you're in, the more you're accelerating, the slower time passes for you. This is literally why 1 hour on that high-gravity planet in the movie Interstellar was equal to 7 years back on Earth.
Now, this isn't just some abstract thing that happens near black holes or in movies. It is happening to you right now. Your feet are closer to the Earth's center of gravity than your head is. That means gravity is infinitesimally stronger at your feet. And that means time is passing ever so slightly slower for your feet than it is for your head. So yes, it's a fact. Your head is technically older than your feet.
And that's really the essence of time dilation. It's a fundamental property of our universe that just completely reshapes our understanding of reality. And it leaves us with one last big question to chew on. If something as basic and fundamental as time can stretch and bend, what else about the world around us isn't quite what it seems? Thanks for joining me on this one.